Okay, so welcome again to the last class of this online problem solving lecture series for NPTEL on the topic Wastewater Treatment and Recycling. I am Akash Saha, one of your teaching assistant, and I am a PMRF research scholar at Department of Civil Engineering, IIT Madras, where I am pursuing my PhD in environmental engineering. So today we will be solving some of the numerical problems. We'll see one by one how to solve them. Okay, so I think someone left the chat. Wait. Okay, anyway, we'll see the problem. So this is the first problem. It's regarding the terminal settling velocity. So you have to find the terminal settling velocity of a spherical particle with diameter 0.5 mm and specific gravity of 2.65 settling through water at 20 degrees Celsius. So it's a simple problem, but sometimes it may get iterative. Like you have to do again and again the steps repeatedly to confirm your assumption as well as to find out the settling velocity as per the conditions. Okay, so please note down the problem. We will solve it now. I hope you have seen the problem. Okay, so this is the first problem for today. So we have been given that the diameter is 0.5 mm and the specific gravity as 2.65 and it is at 20 degrees Celsius. So first we need to know, we should know that the density of water is approximately 1000, or I will take it as 998.2 kg per meter cube, and the viscosity as 1.002 into 10 to the power minus 3 Newton second per meter square. This is at 20 degrees Celsius. So these two values should be known to us. And then for the first case, we have to find the terminal settling velocity, right? So we have to assume something. We will assume that for starting this problem, we will assume that it is a laminar flow. So by this assumption, we can easily find the terminal velocity because we know that the terminal velocity in the case of a laminar flow, only in the case of laminar flow, is G rho s minus rho w d square by 18 mu. So where G is 9.81, rho s is the density of the particle. So we have been given the specific gravity. So my density of my particle will become as 2650 minus 998.2 into d square. D is 5 into 10 to the power minus 4 in meters. I am changing it to meters. Cos square divided by 18 into 1.002 into 10 to the power minus 3. So this is my mu. So in this case, my Vt will come as 0.22 meter per second. So one can say that this is my terminal velocity, but it is my terminal velocity only in the case of laminar flow. So we have to also check whether my flow is laminar or not. So how will we check whether the flow is laminar or not? We will find the Reynolds number. Okay. So we will check the Reynolds number. And Reynolds number, we need the velocity. So first we have to find the velocity. So my Reynolds number Re will be equal to some phi Vt d into rho w by mu. Okay, here this phi term will be equal to 1. This is also known as the shape factor. Okay, since in my problem I have mentioned it to be a spherical particle, so for spherical particle my shape factor will be 1. Because my particle can be of any size, so based on the irregularity of the shape, how close it is to a sphere, we find out through this shape factor. So for the case of spherical particle, it is the same thing, so we will take it as 1. Okay, so now my Re will become 1 into, what is my Vt? Vt is 0.22 into 5 into 10 to the power minus 4 into 998.2 divided by 1.002 into 10 to the power minus 3. So if we calculate this, we will get it as 112. So what does that mean? If my Re value is 112, what does it say about the flow? Can someone tell me? If my Reynolds number value is 112, what does it say about the flow? Are you able to listen to me?
This is not laminar flow.
It is not laminar flow, right? Then what is this? What kind of flow is this? So we have to remember these things. If my Re is less than 1, it is laminar flow. If my Re is greater than 10 raised to power 4, it is turbulent flow. And in between these two values, it is transitional flow. Okay, so this is transitional. Sometimes you may disagree, because in the case of pipe flow, these Reynolds number values will change. Okay, but for this system, we have to know that Re less than 1 is laminar flow, greater than 10 to the power 4 is turbulent flow, and in between is transitional flow. Okay, so what we found out is that we assumed the flow to be laminar, but after calculation we found it to be transitional. That means our assumption is wrong. So we have to do it all over again. So now how will we do it? Now we will find out the CD value. Okay, it's a coefficient CD, this value. So this is basically coefficient of drag, we can say. So based on this CD value, we have to now calculate. So how this CD value will change? In the case of laminar flow, my CD is equal to 24 by Reynolds number. Okay, so please make a note of it. In case of laminar flow, my CD value is 24 by Reynolds number. In the case of transitional flow, I will write it here. For transitional flow, my CD value will be 24 by Re plus 3 by root over Re plus 0.34. In the case of transitional flow, it is this. And in the case of turbulent flow, my CD value will be equal to 0.4. Okay. So now we have to find out the CD value. So since this is transitional flow, I will find the CD as 24 divided by 112 plus 3 divided by root over 112 plus 0.34. So it will come as point 0.84. My CD value is coming as 0.84. So now, once I have found the CD value, now again I have to calculate the settling velocity, right? So now it's a general case. So when we know the CD value earlier in the question, we didn't know the CD value, right? So we assumed it to be a laminar flow. But now we know the CD value. So we can directly use the general formula. We can directly use the general formula for terminal velocity, which is equal to Vt is equal to root over 4 by 3 G rho s minus rho w into D divided by CD rho w. Okay, so this is the general formula for finding the terminal velocity. Only in the case of laminar flow, this equation will change and we will get that equation. Uh, G into rho s minus rho w d by 18 in the case of laminar flow. So we will put the values. So if we put the value into 9.81 into 2650 minus 998.25 into 10 to the power minus 4 divided by CD 0.84 into 998.2. So we will get the Vt as 0.11. Okay, so again now we will check the Reynolds number. Again we will check the Reynolds number. We will find what kind of flow is there. So if it comes to be transitional flow, that means whatever we have done is correct. We will take the Reynolds number as 0.11 meter per second. So we have to repeat the steps. Again, we have to find the Reynolds number, then CD, then VT. So this cycle will go on till we match our assumptions. So are you able to understand the problem? Anybody have any questions in that? So I will give you the final answer. If you do the iteration one or two times, you will get the final answer as RE is equal to 55, CD is equal to 1.18, Vt is equal to 0.10 meter per second. So this is the final answer. But you may have to do one or two iterations. Okay. Anybody has any questions regarding this? Like why we are using CD, why this equation, why earlier that equation? Do you have any questions like that? Or is it understandable? Please, this is the last class. You can ask me the doubts right now.
Sir, what is the formula for settling velocity? This is formula 4 by 3 into G. This
Yeah,
formula is turbulence flow. In the laminar flow, what is the formula?
in the case of laminar flow, this is the formula.
Okay.
Okay.
Can we start from some formulas, sir? This is,
Okay.
this is settling velocity.
You want to know like how we are getting this formula, right? What is the derivation?
No derivation.
Okay.
Only suppose that one question is settling velocity related. है ना? So
Huh.
how many formulas are connected and different? Suppose that rho, rho s is given and the settling velocity is given. Then we found rho w and d. This types some yeah. Otherwise, I want to say the complete formula in any chapter. So in
Your voice is breaking, but what I'm able to understand from a question is Like in most of the questions or any general parameters, you will know the diameter of the particle, right? You will know the diameter of the particle. You may also know the specific gravity of the particle. So, and the conditions, the temperature, like whether it's 20 degree, we can write the temperature. You can find out this. So these three things are easily known. But if we if we don't know whether it's a laminar flow or a turbulent flow or a transitional flow, we directly cannot apply any formula. We cannot directly apply the general formula, because uh, in the general formula, this CD term is coming, right? This CD term is coming. We know rho s, we know d, we know r, rho w, g, everything is known, but CD is not known, since we don't know the type of flow. So at first we will assume it to be a laminar flow, because if we see the laminar flow equation, it just has the d, mu, and rho w, rho s. So all these things are generally known to us. So we will start considering it as a laminar flow. Then we will check whether whatever terminal velocity we are getting, is it satisfying the laminar flow condition. So for that, we will find the Reynolds number. And then if we know the Reynolds number, my CD value is always based on the Reynolds number. You see 24 by RE. Okay, 24 by RE plus 3 by root RE. So always from the Reynolds number only, I will be able to find the CD value. So once I know the CD value, I can put it in the general equation and finally check whether my settling velocity is correct or not. So for starters, since we didn't know anything, whether the flow is, what type of flow is there, and what is my drag value, we started it as assuming it to be a laminar flow. And then we moved into the Reynolds number, then CD value, and then we use the general formula. Okay, is it fine?
Yes, sir.
Okay. Anybody else who has any doubt in this question, or shall we move to the next question? Others? Okay, so if you don't have any doubt, we will move to the next question. Okay, so it's related to the grid chamber. So here it is saying that a grid chamber is designed to remove particles with a diameter of 0.2 mm, specific gravity 2.65. Settling velocities for these particles range between 0.016 to 0.022 meter per second. Now, a flow-through velocity of 0.3 meter per second will be maintained by the proportionating weir. So we have to determine the dimensions of the grid chamber for a maximum wastewater flow of 10,000 meter cube per day. So we have to design the grid chamber. Like, what are the dimensions of it? Length, breadth, and height. We know the particle characteristics, we know the diameter and specific gravity, and also the settling velocities of the particles. A range is given. Why the range is given, we will discuss. And then of the flow through velocity is also given. Okay. So we have to find the dimensions of the grid chamber. I hope you have noted down the problem. We'll see how to solve it. Okay. So in this problem, first we will assume that the cross section is rectangular. Okay. Rectangular, and the depth d is equal to 1.5 times of the width. So this is my basic assumption, that I will make it as a rectangular channel and my depth will be 1.5 times of the width. So what will be my area of cross section? my area of cross section will become W into D or W into 1.5 W or 1.5 W square. Okay, so this is my area of cross section. Now again, my area of cross section I can find out by dividing the flow by what? Flow by what will give me the cross sectional area? Can someone tell me?
That is surface area, Q by
Sorry?
surface area.
No. This
Yes,
is my surface area, right? This is my, cross sectional area. So flow by the velocity. Which velocity, Aditya? Is it the settling velocity or the flow through velocity? We have been given two velocities, right? One is the settling velocity, one is the, so Aditya is saying correct, it's the flow through velocity. See, suppose this is my grid chamber channel, okay? I will make a 3D diagram. Okay, so this is what, this is my width, this is my depth, and this whole thing is my length. Okay, W. So the flow is happening in this direction, water is moving in this direction. So whatever is the, so this is the flow through velocity, flow through what, by what velocity, and the perpendicular thing is my area of cross section. This is my area of cross section. Okay, so Q by Vf, my flow through velocity. So it will come out to be 10,000 meter cube per day divided by 0.3 meter per second. I will change day into seconds. So 60 into 60 into 24 seconds per day. So ultimately it will become as 0.39 meter square. So my area of cross section is 0.39 meter square. So if I put it is equal to 1.5 W square, I will get my width as 0.5 0.51 meter and depth as 0.76 meter. So now I know the depth and width. So these two I have finalized. Okay. So now we will see how to calculate the length. Now for the settling velocity, it is given that it is ranging from 0.016 meter per second to 0.022 meter per second. Right, it is ranging. So for making the calculations easier, I will take the average. So my average settling velocity is 0.019 meter per second. Okay, 0.019. So my detention time, of grid chamber, TD will be equal to depth divided by velocity, because suppose this is the total depth d, this is the particle, it is falling down with vt, so how much time will it take? It will take d by vt. So this is the detention time. So my depth is known, 0.76, settling velocity is 0.019, it will be equal to 40 seconds. So now if I know the detention time, okay, this is my detention time. So my length of grid chamber, so my length of grid chamber L will be equal to the detention time into the flow through velocity. So it is 40s into 0.3 meter per second. It will be 12 meter. So L into W into D is 12 into 0.51 into 0.76 meter. Are you able to understand? Is there any problem with this? Okay, now if you have understood this problem, tell me what is the problem when I am taking the average settling velocity as 0.0919, because some particles are settling with the speed of 0.016 meters per second, some particles are settling with 0.022 meter per second, but I am taking the settling velocity as 0.019 meter per second. So what will be the problem with this chamber? Can someone tell me what will happen? Because let's say there are two particles. Okay, one is settling with 0.016 meter per second, one is settling with 0.022 meter per second. Okay, but I have designed that my, and there are several other particles, the particle size is increasing like this. Okay, I have taken that my settling velocity to be 0.019 meter per second. So what will happen that all these particles will easily get settled, whereas these particles will not get fully settled. Is it true?
Yes, yeah, it is correct.
Right. So we can make it more efficient, or more particles will get settled if I take my settling velocity as the lowest one. Then a longer chamber will be required. Are you able to understand? Because if I change my Vt value here, my detention time will increase. My detention time will increase. If my detention time will increase, my length will increase. So I am giving more length for the particles to get settled. So in this case, if I take the settling velocity to be the smallest one, I will ensure that all my particles will get settled. Whereas in this case, not all particles will get settled. Some will get settled, some will not. It will flow through. But to control our cost, to control our time, we don't always go for 100% removal of these particles. Okay, we don't need. Maybe in the later stage, it will get removed. These particles are too small to be removed by grid chamber. So we will make sure that in the next stage it will get removed, or with some other treatment facilities it will get removed. Right? Are you able to get the problem? So it's not only about solving the problem. We have to analyze like what are the assumptions we are making with each of the problems. Because for each of the problems, to make the calculations easier, to make for it for lesser cost, for lesser time, we will make certain assumptions, but we should know the reality behind those assumptions. Okay, what implications it may happen? Suppose your designer tells you that you have to ensure 100% removal, then you have to take the least settling velocity of the particle, or do something such that the particle size will increase, they will agglomerate, the particle size will increase, and hence the settling velocity will also increase. That's why we add sometimes the chemical coagulants, all those things. So it will make flocks. It will make some flocks, the particle size will increase and the settling velocity will increase. So again, with lesser time, we can more effectively remove all the particles. So these are all small nuances that we have to do to design any reactor or any chamber. Okay. I hope you are able to understand all these things, because these are some critical things for design. Okay. We will now go to the next problem. Okay. So this is a graphical type problem. We'll discuss how to do this, but first see. So it says a settling analysis is run on a type 1 suspension. The column is 1.8 meter deep. Okay. So I will go through the question again. It says that a settling analysis is run on a type 1 suspension. The column is 1.8 meter deep and the concentration versus time data is mentioned in the table below. What will be the theoretical removal efficiency in the settling basin with a loading rate of 25 meter cube per meter square per day? So are you all aware with what is settling analysis or how to do the settling analysis experiment? Do you know? Please let me know if someone is aware or not. If you are aware, please send a thumbs up. Then it will be easy for you to understand the problem. You are not aware. Okay. So I will, have you taken down the problem? You please take a screenshot of this problem. We will solve it now. I will briefly discuss what is this settling analysis and then we will see how to solve this problem. Okay. Suppose this is a settling column. Okay. In that we have poured our sample. Whatever sample, many particles will be there. It will be full of particles and I am considering it to be a homogeneous, like it is well stirred, all the particles are homogeneous throughout. And I will make a sampling port here from where I will be able to get the samples. Okay, so now we have been given the time, it is in minutes, and we know the concentration, milligram per liter. So what is this concentration? So suppose we are starting at 0.00 minute where my concentration is given as 300 milligram per liter. So 300 milligram per liter of concentration of particles are there inside and we have started the experiment. After some time, the particles will start settling and I am considering it to be type 1 settling. Type 1 settling means discrete settling. They are not forming any flux. They are not doing any compression. Individually, each of the particles is settling by itself. It is not influencing the other particles. So this is a type 1, type 1 settling. Okay. So after some time, what will happen? What? So after some time, what will happen
Concentration
to the
decreases,
concentration? Hello?
decreases, decreases.
It will start decreasing, right? The concentration will start decreasing. So suppose it is 60, the concentration decreases, it is given as 189. At 80, it is given as 168. Okay, at 130, it is given as 156. At 200, it is given as 111. 240, it is given as 78. And at 420, it is given as 27, right? So we will say, we will find the mass fraction that is remaining. Mass fraction that is remaining. So we leave the 0th minute thing. So how much is remaining here? Remaining mass fraction is 189 by 300. So what will be the mass fraction remaining? It will be 0.63. Okay, similarly, we will find all the mass fraction remaining. 0.6, 0.56, 0.52, 0.37, Oh, sorry, there is one more number is there. I will write it here. After 80, we have one more. We have this 100. This is the time, or I will rub it off. Wait. Hundred, 130, 200, 240, 420. So it is 150. Sorry. At 80, it was 180, 100, 168, 156, 111, 78, 27. So these mass fractions will be 0.6, 0.56, 0.52, 0.37, 0.26, 0.09. So these are all my mass fractions. Okay. And at last we will find the settling velocity. Vt. So this column height is given as
1.8 meter deep.
1.8 meter. 1.8 meter. So again 1.8 divided by 60, we will get it as 3 into 10 to the power minus 2 meter per minute. So this was 60 was given here. So 1.8 divided by 60. So 3.8. So I will write it as Vt into 10 to the power minus 2. So here I will just write as 3. Just the whole number I will write. So for this it will be 2.5, it will be 2, 1.55, 1, 0.83, 0.48, 0.48. So these are all the settling velocity. So now we have to plot a graph. We will plot a graph between the mass fraction that is remaining, that what we have calculated, these values, this x values, mass fraction remaining, and in the below we will add the settling velocity Vt. We have to plot a graph. So with this x and y values, if we plot a graph, we will get a curve somewhat like this. We will get some S-shaped kind of curve. Okay, S-shaped kind of curve. Now, in the question, it was given that my loading rate, okay, or the surface overflow rate was given as V0 was given as 25 meter cube meter square per day. So which is nothing but 1.74 into 10 to the power minus 2 meter per minute. I am just changing seconds to the day to minute. So it is 1.74 into 10 to the power minus 2 meter per minute. So everything is in terms of meter per minute. So what will happen if any particle has the settling velocity greater or equal to this surface overflow rate? It will get settled 100%, right? So we have one overflow rate, and if you are getting 100% efficiency on the settling, then all the particles which have the settling velocity equal to or more than this will get 100% settled, right? Suppose this V0 value is somewhere here, somewhere here. So we will make a vertical line and we will see what is the mass fraction remaining. So this mass fraction value is around 0.54. So above this, the particles are getting settled 100%. Okay, 100% settling is there. But below this line, the particles will get settled only partially because the settling velocity is lesser than the overflow rate. Okay, so how much partially it is getting settled, we have to find out with the help of finding the area under this curve. So if we are able to find the area under this curve, we will be able to calculate the total mass fraction that has been removed from the system. So now this has to be done by either integration. You find the uh, equation of this curve and find out the area under the curve, but equation of this curve will not be known in graph. So what we will do, we will divide this area into small strips and then we'll calculate the area. I will show you how to do this. So what we are doing is we will make some small strips. Okay, so I've divided this area into small strips. Now I will, this is basically each of the strips I will consider it to be a rectangle. Suppose this strip I am talking about. This strip I am talking about. So if I add all these strips one by one, if I add all these strips, I will get this area, approximate area I will get. So that's what I have to do. So in the question or in the solution part, how they have done, I will simply do in the same way. I will divide the strips. So this width they have given us 0.06. This width again 0.06. This width they have given 0.1, 0.1, 0.1. This is 0.06 and this again 0.06. Now the width is fixed. I have divided the strips. I have given as 0.06, 0.06, 0.06 and some 0.11. Okay. Now what about the length of this strip? Because on one side the length is up to this much and on other side the length is up to this much. So what we will do? We will find out the midpoint of these two lengths and I will find the length of this. I will find the length of this. Again, midpoint for the next strip, this is the midpoint, I will find the length. This is the midpoint, I will find the length. This is the midpoint, I will find the length. Okay, so suppose this is some x, y, z, these are all my lengths. So if I multiply this width into the length, I will get the area. So I will quickly do this. So this is the delta x, that is the width value, what I have given. So 0.06, 0.06, 0.1, 0.1, 0.1, 0.06, 0.06. So these are my width. And what is the length? Length is nothing but the VT value. Length is nothing but the VT value. So for the first one, my VT value is up to this much. For the first strip, up to x. So that is equal to 1.5. For the next, my VT value is up to y. So that is actually on the graph as 1.22. Then 1.85, 0.7, 0.48, 0.16. So then I will do, so the area of each of the strip I will find out delta x into VT. It is 0.09, 0.07, 0.1, 0.09, 0.07, 0.03, 0.01. And add if I add all these values, I will add all these values, I will get the total area under the curve, that is the summation of delta x into Vt, it is equal to 0.46. Okay, so what we have done, we have told that this V naught, so if any settling velocity is above this V naught, it will get 100% removed. So suppose the total is 1, so 1 minus 0.54, that much value will be removed totally, that will be removed from the system totally, and rest, this area under the curve will be removed. Okay, so the total, so the overall removal efficiency x will be equal to 1 minus the x naught value, that is 0.54, plus all the summation of all the Vt divided by my settling velocity. So it will be around 1 minus 0.54 plus the summation under the curve divided by my settling velocity, that is 1.74. So 0.46 plus 0.26, it will come as 70.72. So 72% particles will get removed. So now tell me, are you able to understand this problem? Is this clear for you? Or you have any questions? Hello, are you able to hear me?
Yes, sir. Here.
Did you understand the
Actually,
problem?
yes, sir. But we distribute the area and find point 0.1 and 0.06 is the width of the small rectangular
Yes,
shapes.
yes.
How can this find, sir?
Okay, you are asking like why did we take it as 0.06 and zero point 0.1? Are you asking this?
Yes, sir. Yes.
Okay, so the major idea behind this is, suppose we have any S curve, right? This kind of S curve, whenever it is there, so what we see, like see, in the starting portion, this area, my slope is very high. Okay, my slope is very high. This area, my slope is not that much. And this area, again, my slope is very high. Okay, so if I take big strips here, my error will be very large. My error will be very large. Whereas if I take big strips here, my error will be very less. So what we try to do in the middle portion, we try to keep the width as more, because the slope is not that much. Whereas in the case of starting point, these points and these points, since my slope is more, I will keep the width minimum. So this was the rationale behind it. Maybe you can do it as 0.05, zero point zero 0.05, then in between you take it as 0.15, 0.15. Again, in here you will take it as 0.05, 0.05. Or throughout you take 0.01. Very thin strips. But then your calculation will increase. Here we are just approximately calculating the area. We are not worried to find out to a very minute detail. We are not going to find out in like in decimals or something. Approximately what is the removal. So that's why those strips are taken like that. But if you want to fine tune your answer, you take very thin strips. Very thin strips you take. Then your calculation will be very easy. Now your calculation will be complicated, but you will get exact value. So are you able to understand this? What type of questions and pattern of the see the question pattern will be similar to your assignment problems. Okay, so whatever type of questions you have done in assignment, only those type of questions will be asked. Number of questions I am not sure. I think if it is for 100 marks, you will get 50 questions. I am not sure about the number of questions, but the type of questions will be exact, it will be MCQs only. There will be no subjective types. I am solving the subjective questions here just to increase the understanding, because if a big subjective problem is there, they will make small part of it and give it as MCQ problems. So that's why I'm solving subjective problems here, not with the motto of solving questions only in NPTEL exam, but it will help you for future also. But in the exam, mostly no, always only MCQ questions will be asked, or maybe that numerical type problems like very small numericals where you have to give the numerical value of the answer in the space given. Okay. Anybody else who has any doubt in this question?
So,
Others are
sir,
okay?
this is the exemption like thing, na? This is the S curve, and we distribute the small fractions, and according to the chart, है ना? We assumption this value is this, and find the area, and after the find the area, we calculate.
Yes, yes. So it's basically your discretion, like how you want to divide the area. Okay. So whatever width you take, see the length value will depend on your uh, average of your starting length and ending length. Okay, that will be constant. But the width of the strips is your discretion. If you want to calculate very minutely, you take very thin strips. If you just want to do like an approximate value, you take a wider or thicker width and solve the problem. It is your response, like your discretion. You don't have to worry about that. Answer will be more or less same. Okay, someone may get 74%, someone may get 71%, but I don't think much difference will be there if you are doing it properly.
Okay, okay. Thank you, sir.
Okay.
Sir, please below the slide. Actually, I want to know settling velocity. Just drag the
Settling
slide in.
velocity, like
Just
what is it? I am not able to hear your voice. Can you speak a little bit louder?
actually this value 0.54.
Ha.
How it is come?
Oh, 0.54. See, it is in the question. I will open the question once more. See, in the question, it is given what will be the theoretical removal efficiency in a settling basin with a loading rate of 25 meter cube per meter square per day. Okay. So this 25 meter cube per meter square per day is the overflow, surface overflow rate. Okay. So if the settling velocity is equal to my surface overflow rate, 100% of the particles will get removed. That is the basic assumption in any reactor. Okay, in any settling type of reactor, this is my assumption. Okay, so this 25 meter cube per meter square is nothing but meter, right? So 25 meter per day is equal to 1.74 into 10 to the power minus 2 meter per minute. What I have found out. This. So this value is equal to 1.74 into 10 to the power minus 2. So this point on this y-axis, where it will be here somewhere 1.72. Let it be here. So I will draw a vertical line to the graph, to the curve from here. And then from this point, I will extend a horizontal line and see. So this is my point of intersection. This is my point of intersection. So this point of interaction is 0.54. In this graph, it is 0.54. So above 0.54 fraction, everything will get removed. So that's why I've written 1 minus 0.54. So that 0.46 mass of particles will definitely get removed 100%. But below this curve will get removed partially. So this was the assumption. Okay. I hope you understood it. And okay, we will see the next problem now. Yeah, so this was the curve. I have made this book picture also. So here you can nicely see like how they have differentiated the various strips. Okay, they have taken the width as 0.06, 0.06, 0.1, 0.1, and for the length they have found the midpoint and taken the length, and correspondingly they have solved the problem. So this is the clearer picture. Okay. Okay, so now NPN type of problem. So we know that most probable number, you have to find the NPN per 100 ml of sample. What is my NPL? Which refers to the coliform organisms. So it says a water sample is analyzed for coliform organisms by multiple tube fermentation method. The results of the confirmed test are as follows. So they have given some sample size. So for 3 sample size, out of 5, how many are positive tubes and how many are negative tubes? So do you know what are these positive and negative tubes? Do you have any idea about NPN test? Or should I give a brief idea about this test? Are you aware about this NPN test?
Please give a brief, sir.
Okay, I will just give an introduction to this test. So what we do, we try to see whether my sample, suppose I have collected one sample somewhere from any lake or any pond somewhere. So it has number of microorganisms. It may or may not have number of microorganisms. So I will try to check whether my sample, like how many microorganisms are there. So what will I do? I will take 15 test tubes. 15. Okay. Suppose. Okay. So suppose in the first test tube, I am giving, in the first 5 test tubes, I am giving 1 ml of sample. In the next 5, I am giving zero point 0.1 ml of sample. In the next 5, I am giving 0.01 ml of sample. Okay, so in each, I have given some samples. So all these sample may or may not contain the bacteria. It's a probabilistic method. It's a probabilistic method. It is not a absolute, like we cannot absolutely find the number of coliforms, but probabilistically what how many organisms are there, we will find out. So we will give the we will pour the samples in the test tubes, and then we will provide the nutrient for this bacteria to grow. We will give nutrient in all the test tubes. In all the test tubes, we will give some nutrient or some food for these microorganisms to grow, and then we will keep it under incubation. Incubation means at some constant temperature, maybe for fecal coliform and for total coliform, the temperatures are different. One is I think around 30, one is around 35. So something like fecal coliform or total coliform. So based on the experiment, we will keep it as some, suppose I am keeping it as 35 degrees Celsius, constant temperature for it to grow. And also everything will be plugged with a cotton plug before putting it into the incubation. Okay, so when I will put these samples and this media, after 1 day, what will happen? Some gases may be produced inside these test tubes. So these gases will correspond to the growth of my microorganisms. If gases are produced, it means that it has the microorganisms. So to see those gases, okay, so to see the gases in each of the test tube, after filling the sample and the uh, nutrient, I will put a inverted Durham tube. Inverted Durham tube. Okay, this is the cotton plug. Before putting the cotton plug, there will be an inverted Durham tube. So if any gas is generated inside, it would get collected here. It will get collected here. So after 1 day or maybe after 2 days, we will check like in how many samples I am getting that gas particle, that gas formed inside the inverted Durham tubes. In each, the small Durham tubes will be there. Okay, so I will count like out of 5, there is 5 1 ml sample test tubes. So out of 5, how many has hydrogen? How many has the gas? In this out of 5, how many have the gas? In this out of 5, how many have the gas? Okay, that I will calculate. So if we see the question now, so here the sample sizes that are given is 0.01. That means for the first 5 test tubes, they have put 0.01 ml of sample, then 0.0.001, then 0.0001 ml of samples. Then out of 5 tubes, all 5 tubes in the case of first one, it is getting the gas. So it is a positive tube. And 0 gas were like 0 negative tubes are there. Okay, so out of 5, all 5 are getting the gases, means all are positive tubes. Then for the next 5 set, for 0.001 sample size, there are 3 positive tubes, 2 negative tubes. Similarly, for the last one, there is 1 positive tube and 4 negative tubes. So are you able to understand what are these positive tubes and negative tubes? It is nothing but if gases are produced in the tubes, it is a positive tube. If there is no gas out of 5, so it is a negative tube. So like that it is given. Now how will I, now if I know this thing, how will I get to know like what is my NPN value? So what people have done, many experiments, many repeated experiments with different amount of samples, and they have found out all the combinations. So for this set of experiment, my combination is 531. My positive tube combination is 531. So if my combination is 123 or 135, 532, 534, so for every possible combination, they have found the NPN index value with experiments. So that's what the next table is given. So it says the most probable number of the coliform organisms for the above results is to be obtained using the following NPN index. So they have made a NPN index. But now again, we have to see that this NPN index is given for, if you see closely, it is given for 10 ml, 1 ml and 0.1 ml of sample. Whereas in our experiment, we have taken sample as 0.01, 0.001 and 0.0001. But the NPN index chart that is provided to us is for 10 ml, 1 ml and 0.1 ml. So we have to make some dilution correction. Okay. So for 4 combination positive tubes, they have given like 024, 135, 420, 531. They have given the NPN index values. But this is a very big chart. For all possible combinations, the chart is there. Okay, but for this question, I have just shown these 4 values only. But in the real chart, all the possible combinations are there. So we will see how to solve this problem. So first, we have to find out the combination of the positive tubes. So here it is 531. Okay, so now we will check the NPN index. So for 531, the NPN index is 110. If you see, for 531, the NPN index is 110. That is 110 coliforms are present per 100 ml of sample, or for 100 ml of the system. Okay, but now we have to change the dilution correction. So in the point C it is written, but the sample size is for 0.01, 0.001 and the NPN table is given for 10 1 bin. Hence, the result has to be multiplied by 10. So you take the numerator as the highest value of your NPN index table and denominator as highest value of your experiment sample volume. So it is 10 by 0.01. So 1000 times it has to be multiplied. So my final NPN index will become as 110 into 1000. Okay, so it is 1,10,000. Suppose I did the experiment for 100, 10 and 1 ml. Then my NPN index has to be divided by 10. Are you able to understand? Others? Others, are you clear with this concept? Okay. So this is the overall picture of NPN index. We will see the positive tubes, what is the combination for those tubes, and then we will find out the NPN index. We will see the NPN index and find the NPN value, and then we will multiply or divide with the necessary dilution factor. We will get the result like that. Again, now suppose for some combination you are not able to find the index value. Like 531 is given, 533 is given. You are not having for 532. You are not able to find it from the chart or something. See, why we take only 3 samples is we could have done it for 1 sample also, but some but we will check. Suppose if my system is diluted 10 times, if my system is diluted 100 times, what is the possibility of getting a microorganism there? So we will check for 3 serial dilutions. Okay, so it's just a confirmation, like 10 times, 100 times dilution also it is there. And all this chart, they have done the experiment for 3 serial dilutions. Okay, it's just a confirmatory thing. Okay, now there is one more equation called the Thomas equation. So Thomas equation, if you know the positive tubes and negative tubes, number of positive tubes and number of negative tubes, you can directly apply this formula and find out the NPN value. You don't have to refer any chart. Suppose you don't have the chart, yeah, it can be 4 also. You can do for 4. Like here itself, I have given the Thomas equation. For solving the Thomas equation, I have given the 4 sample sizes. But the NPN index chart is given for 3 serial dilutions. So that's why for experimentation also, we do the 3 serial dilution. Okay, but you can see in the case of Thomas equation, if you don't want to use the chart, you can directly use this Thomas equation. So how it works? So it says that NPN value is equal to number of positive tubes into 100 divided by root of ml of sample in negative tubes into ml of sample in all tubes, not positive, it's all tubes. So for this table, how many are my positive tubes? So number of positive tubes will be equal to 4 plus 2 plus 1, that is 7. Then ml of sample in negative tubes. So how much sample in negative tube is it there? So for the first 1 into 10, 10 ml, 1 sample is there negative. 1 ml, 3 samples are there. 0.1, 4 samples are there. 0.015 samples are there. So we'll just add it. It will come as 13.45. Then ml of samples of all tubes. So we have 5 number of tubes. So 5 into 10 plus 5 into 1 plus 5 into 0.1 plus 5 into 0.01. So the total ml of sample is 555.55. Right? So like that way, we got all the values. We will put inside the Thomas equation and we will get the NPN value. So here the NPN value is coming out to be 26. So if you see, if you calculate with the Thomas equation, same question you calculate with Thomas equation and you check in the uh, MPN index also, it will be more or less same. Not much difference will be there. Slight difference will be there, but not much. So this is the Thomas equation. Okay. So if you don't have the chart, you can directly use the Thomas equation and find out the values. Is it clear? Anything to be explained now regarding this NPN test? Others? Okay.
Compared to these two, which one will be the more reliable?
Uh, See, people mostly use the NPN index as far as I know. If they are not able to find that combination thing from the NPN index, they use this Thomas equation. Or if they don't have the chart, they will use the Thomas equation. But the first preference I think is given to the NPN index because it's experimentally derived. So I think they are using the chart mostly. Okay.
Okay, sir.
Okay. I hope it is clear. Okay, so now we will do a population forecasting problem as you have requested. So we will quickly see like how to do the population forecasting methods. So we will use the same data set to find out the population through all the methods. So for 1961 to 2001, all the populations are given. So we have to find the population at 2041 with all the three methods. It's a very simple problem. We'll just go through just a quick recap so that you are clear of it because it was requested from you only regarding this population forecast. Okay, so first we will see the arithmetic increase method. So you have the year, you have the population. We don't have to do anything. We will find just the change per decade or whatever timeline is given per year or per decade, whatever timeline. Mostly for census values are given per decade. So we'll see the change. So in the third column, you can see I have mentioned the change. So from 71 to 61, 81 to 71, what is the change? I have mentioned. Then we will do the sum total of the change. So it is coming out to be 75,000 and then 75,000 divided by 4 we will do and we will get the average. So arithmetic increase, what does it say? It will say that each year the average amount will get added to the population. Each decade, not each year, each decade, the whatever average increase was there previously, that much will get added. So the last population is of 2001. So the population was 82,149. So we have to find out for 2041. That is after 40 years or 4 decades. So 4 times the average value will get added. So 82,149 plus 4 times into the average value will give the population in 2041. So mostly for new cities and all, we don't use this arithmetic increase method because
Because the value will be less compared to other.
exactly. So new cities means it will be developing more and more people will shift. So we cannot go for average. So for new cities, we have to news and like suppose it is an old city, but a new IT sector has been developed. So IT sector means more and more job locations will be there. So people will start shifting to that city. So at that time also we cannot use arithmetic increase method. We have to go for some geometrical increase or incremental increase method. So based on your situation, now we will see how to use the geometric increase method. Okay, so in the previous thing we have find the change. Now we will find out the percentage change. It is nothing but the like 6460 was my change. So with the respect to previous population, what is the percentage change? Okay, so 94% has increased. Then 1.7, not percentage, it is 176% then. Okay, but in terms of the decimal values, it is 1.76, 0.585. So in the case of geometrical increase, we will directly put it as, it is same formula as the compound interest. Okay, compounding factor will come, it will go into the power, we will find the geometric mean. How we will find the geometric mean? We will multiply all the percentage changes and we will take power to be 1 by n. How many? So this is the geometric mean. We found it as 0.795. So the population will be 82,149 into 1 plus the geometric mean to the power of number of decades. So 2041 means 4 decades. So see what the variation, how drastically it has increased. So in the geometric method, the increase will be too high. So we have to be careful. We have to keep a check, like whether you really think that population will increase that much, or if there are multiple job opportunities, tourism opportunity, everything is there, then the population can increase that drastically. So in those cases, we can use the geometric method. Whereas if the growth is intermediate, you're thinking no, it will not be like arithmetically increasing, or it may not be that much high, so we can go for the incremental increase. So now again, in the case of the incremental increase method, we will see that there is a incremental change. We will find the change in change. Okay, so in the arithmetic method, we have found the change like 6,460, 23,000. Now, what is the change in change? Okay, so again, it is just subtracting the lower value, like higher value from the lower value, or the population in the latest year minus the previous population, not higher, lower. It's what is the change in my change. It can be positive, it can be negative also. So we will find the total of all the changes, total of all the incremental changes, average of all the changes, average of all the incremental changes. And then the formula is very simple. The last known population plus the number of decades into the average change plus n into n plus 1 by 2. That value 10 which is coming in the formula is n into n plus 1 by 2. That is 4 into 4 plus 1 by 2, and then the average of the incremental change. So it will give a intermediate value between the arithmetic and the geometric increase. So in the arithmetic we got as 1.5 lakhs. In geometrical increase we got it as 8 lakhs, around 8 lakhs. Whereas in the case of incremental increase it is around 2 lakhs, 2.15 lakhs. So this was about the arithmetic increase, or this was about the incremental increase method. So I hope these methods are clear. These are very simple but frequently asked questions. Definitely in GATE or in your NPTEL exam, it will definitely be asked. These are frequently asked questions.
Normally, these three methods are using for calculation, or because actually, what I mean to say, normally for this calculation, there are so many, near about 10 system, I mean, methods are there. Incremental increase method and changing rate of increase method also there, are graphical method also there, comparative method or curve line method also there.
Yeah,
Decreasing
so
rate. Yeah, all these are normally it is not using, sir. For calculating
no, no,
for the
no,
wastewater, normally using these, mainly using these three
no.
mathematically.
These
Uh,
three are, to be honest, these three are methods are used for these kind of to be asked in exams and all. But actually, people will see the uh, actual site conditions, like in a city and all, how the population has been like. Best is the graphical method. Okay, graphical method will give you the exact picture of the city or anything. And there is also that S curve, that logistic curve method. Okay, so new city, mediocre city, old city, how the population is increased. Those methods are much accurate than these methods. These methods are just for rough calculations, as far as I know, or maybe for your exam point of view these methods are there, but other methods are also very well used based on the requirement or based on the type of system. Suppose you want to develop a wastewater treatment plant, maybe people are using one type of method, they are want to use some road networks, so for that they are using some other methods. So based on their own experiences and their own conditions, people are choosing different methods, but those methods are also definitely used. The logistic curve method, the graphical method are very much popular. Okay, so don't think that those methods are not used, but for exam point of view, because for those methods to be used you need a lot of data. In exams, not much data is provided to you, but for those methods a lot of data is required. Okay, so
And sir, what about peak factor?
what which one?
Peak factor.
Peak factor.
Yes, sir.
Yeah, peak. See, this is for this population increase, right? Peak factor we will see, like uh, what when do we use the peak factor? Like suppose the we are trying to calculate the wastewater flow. Okay, now this wastewater flow will not be equal throughout the day. Sometimes it will be high, sometimes it will be less based on your usage. But we cannot, but we want our system to be robust so that it can work throughout. So what we will do, we will take the average flow. We will, based on our population or our experience, we will multiply with some peak factor so that suddenly if more flow comes, our system is stable. So in population forecasting, we won't use the peak factor, but to design any particular element of our wastewater treatment plant or water treatment plant to make it safer in the case of unforeseen uh, circumstances, like too much flow is coming, or like suppose everyone is using water. So at that time, everything will come as wastewater. So the flow will suddenly increase. We cannot go with the average wastewater flow, right? So at that time, we have to use the peak factor and design it. Okay.
These type of questions are also important for the point of exam view.
I am not able to get you. Sorry.
Peak type of peak factor type of questions are
Ha.
important for exam view.
Yeah, definitely, definitely. Sometimes they will mention the peak factor, so you have to incorporate the peak factor in your design and then solve the problems. You might have seen in some of my problems also, I have given the average flow, I have given the peak flow also. So if peak flow or peak factor is given, you have to multiply with the average flow and then solve the problems. Okay. Abdul, you have anything, any doubt?
So regarding this quality of water, I mean for the after wastewater treatment, even for advanced treatment, then that water suppose it is using for recycling purpose.
Mhm.
In which category normally it is coming? Quality of water, just like a chemical water or potable water or palatable water, wholesome water, polluted water, contaminated
No, no.
water, and like that, that in which quality normally it is coming, under which quality it is coming,
No,
this
so
recycled.
it depends on how much recycling you are doing, right? Suppose in in Indian context also, they have defined as type A, type B, type C, type D water. Okay, so for each type there is a discharge standard. There are guidelines, like we will say it as a type A or type 1 water if it maintains this much of BOD, this much of COD, this much of microorganisms, this much of heavy metals. So guidelines are given. Okay, randomly we can say whether this water is clean or not clean, wholesome or potable, palatable. But to be very specific, we have to uh, check all the quality parameters and then decide based on our diet guidelines. Okay, but mostly if you are going for advanced oxidation methods or tertiary methods, that means it's a very good quality water. Mostly it will be potable water also. But again, we have to be very cautious. We have to see all the parameters. In in water quality parameters you have seen, there are many physical, chemical, and biological parameters. So you have to analyze all those things. We have to see what values you are getting, and then we will match with the guidelines and see what category it is falling into. Until and unless we are not uh, doing the quality analysis, we may not be able to judge whether this water is uh, what kind of water it is. Okay, so it all depends on the final effluent standards that is maintained.
Okay, sir.
Okay. So you try to see like IS I think 10200, or I am not able to, the drinking water standards. You check that standard. You see how much amount of all the minerals, all the BOD, COD, microorganisms, what are the different standards are given. You have to remember those things. It will be required for drinking water, for bathing, for swimming, for pisciculture, for irrigation. What are the different standards? You just make a note of it. Then you will be able to judge whether uh, this kind of water is suitable for this purpose or not. Okay. Anything else regarding the? I think that settling velocity type 1, type 2 settling is a bit tricky. You you don't expect very difficult questions in the exam, but for understanding it's good. You can you can refer to this book. Okay, this is the PV and Rowe book, Environmental Engineering by PV and Rowe. This is the Indian edition. You can also purchase it from uh, some Amazon, or you can get a second-hand book. Okay, it's a very good book for water, wastewater, solid waste, and air. Everything is there in this. Not in much full detail, but whatever is required for BSc, BTech, MSc, MTech level, it is there. All the questions, standard questions which I solve, or what you see normally all around here and there, you can. Okay, I will just write it. See. This, so this is environmental engineering. The book name is just environmental engineering. The authors are Howard S. PV, Donald R. Rowe, so these are the authors. So basically, people call it as PV and Rowe, PV and Rowe book. So this is the common term. Anyone is saying PV and Rowe book means this book, Environmental Engineering, PV and Rowe. So PV and Rowe are the two authors of this book. And one
Yeah,
more.
this is foreign edition, foreign edition or Indian edition?
No, this is Indian edition. The blue color is the Indian edition. Foreign edition means it's a pinkish red or pinkish book. Okay,
Yeah, yeah.
since it is that that
What?
that that book is very costly actually, so
Yeah,
that's why
yeah.
I've purchased this book.
Okay, I also gone through some books. I having one book, this sewage treatment and disposal and wastewater engineering, environmental engineering volume 2. This is done by Dr. P. N. Modi. Have you aware
PN
about
mode.
it, sir?
Yeah, that
That
Indian.
I am using. Yeah, they're having a lot of problems and all these things there. But compared to the other book, that much,
Yeah.
it is not elaborate.
Basically, mostly in Indian authors' book, you will not find in much elaborate details. Whereas this PV and Row books, and one more book I will show you. If you want to study wastewater engineering in full detail, like everything about wastewater engineering in detail, this is the Bible. You can say. Okay, this is, and I will write is the wastewater engineering by Metcalf and Eddy. Metcalf and
Yeah,
Eddy.
I know about that book. It's a very expensive. It is
Okay.
very expensive book also.
Metcalf and Eddy. So
But
if you,
I think we can
No,
download from the net also. I think because there is some
you
thesis there.
no. In Indian publication, it's very cheap. At the time when I purchased, it was 500 rupees.
you can get it. I also got it around around in sale around 800 900 rupees. So you can get it also, but most of the times it is not available on the Flipkart or Amazon. It is not available, but you can always check if you get it, and if you really want to uh, study in full detail, this book is very good. Okay. Uh, and otherwise for your BTech and MTech level, MSc level, PV and Row book is enough. I think you will get everything in this. What else? Any other doubts or anything you have?
Excuse me, sir.
Yes, tell me.
When we get our hall ticket,
Sorry, your voice is not clear. Can you come again?
when we get our hall ticket,
Hall ticket. Actually, I am not aware about all those things, but you will get it. When is your exam?
28th.
28th,
This
right?
week.
I think before 1 week it will be available. 1 week it
Okay.
will be available.
Okay, thank you.
Yes, Mohammed, are you trying to say something?
No, no, sir.
Okay, so thank you everyone and best wishes for your future. If you want to connect with me sometime, you can drop a mail in my email ID saha19akash@gmail.com. Okay, and if you have any feedback for me, you can tell me right now, or you can write in the chat box any feedback regarding my teaching or the content that I covered and how can I improve. This is my email ID, Serena. You can see saha19akash@gmail.com. Okay. So if you want to say something or any feedback regarding my teaching or my contents or how can I improve in future, if you want to say something, you can tell me right now, or you can mail me also if you don't want to say anything right now. Just let me know because this is one of my first class experience with you guys. So I'm happy I'm able to share something, share some knowledge with you, and thank you so much.
Thank you, sir.
Okay, thank you very much, sir. Anyhow,
Thank
I
you.
am very
Thank you very much, sir.
happy and I am.
Yeah, tell me.
Anyhow, from my side, I am very much appreciating, because your class was very nice and, it's very audible and very much attracted also. Anyhow, I am a senior citizen also. I am just interested to just to update my knowledge and all these things. I already done two, three, four courses. I already did from NPTEL. One
Okay,
it was
okay.
in geotechnical engineering. I got it. Dr. Singh was the Bombay IIT. Then after I done GPS global position survey. That also got certification. Digital survey and mapping also I done. This is my fifth, I think. This
Oh, great,
recycle.
great.
I am still continuing. I am already some retire age also there. Even though I am very much happy to continue and
That's
reading
very
and
good.
all these
Nice
things.
to hear.
Okay.
Thank you. Thank you so much.
And just briefly, I just explain what is my interest. I am not going for. Previously, I was working outside India. More than 20, 40 years I was in outside India, and I have lot of experience for the construction activities and all these things. But still, I am still interested for just forget updation and all these things. Even some if my knowledge or something I can participate to somebody else, I am be happy like that only. And
That's
that's why
so good.
still I am continuing. I am looking for this some courses. If there is some time, then I will continue. There is no problem because there is no limit for the age.
Sure, sure. I am very happy to hear it from you. Thank you
Okay,
so much.
okay, sir. Thank you very much. Have a nice day.
Thank you so much. Thank you so much. Thank you everyone for your feedback and comments. I really appreciate. And it was very nice teaching you all. Like constantly you are coming to the classes and you are with me. So it was very much appreciated. So it gives me confidence also to teach further. And I'm happy that I'm able to help you in some way, in some small way. So together we can share knowledge and grow together. So it was very nice session for me. Thank you so much. Thank you.
Thank you, sir.
Okay, okay,
Thank you very much, sir.
okay.
Sir,
Tell me.
one thing, Manoj sir is a very matlab, good explain in whole lectures
Yeah,
because I am just participating two courses, है ना? But two and three courses. So the best subject is wastewater recycling, treatment and recycling, because explanation of Manoj sir
yeah,
and
yeah.
you are and one and another live session I just joined. So overall experience is very good, sir. Very
Thank you.
good.
Thank you.
Because I am just a power plant chemist and
Okay.
15-year experience.
Okay, great, great.
So this is the great knowledge for me.
Thank you. Thank you so
And
much. It's nice to hear.
your explanation technique is also very good, sir.
Thank you. Thank you. Thank you so much.
Thank you so much, sir.
Yeah. Yeah, so actually the subject itself is very, very interesting. This wastewater treatment and recycling. We even while teaching also we can learn so much things, and while discussing things we can get to know many things. So it was a wonderful experience. Okay, guys, if you don't have anything to say or anything to ask, you can leave the session. I am done from my side. Okay. Yeah, sure, Sarkit. Maybe next semester, if I get a chance, uh, we will see like which subject is coming. Uh, they are offering. If possible, if I get a chance, I will be definitely be a TA for this, for that one. Saket, are you also studying for GATE exam? I think you are studying. Yeah, sure. We'll join. Okay, great, great. Yeah, keep practicing. GATE exam is all about your practice, numericals. I think you will do very good. Thank you, Aditya. You can leave the session. Thank you so much. Thank you, Sakit. If you have any queries later also, you can drop me a mail, okay? No issues.